Welcome to today's workshop. I am Ayhan Akray and I work as a technical consultant in Allplan infrastructure. And today we will go into detail how to model the precast girder bridges from geometrical modeling to analysis modeling. And today, as you may know, precast girder bridges require many steps. Like we will start with geometrical modeling first. Then we will together explore how to use this geometrical modeling and transfer this to analysis modeling. And in their analysis, as you may know, precast girder bridges require many stages, like a fabrication process, lifting process, a construction on-site processes. And we will together precisely model them. And then you will see how to evaluate the results, and we can even see how to create the calculation reports in today's workshop. So after creating this workflow, we will also see how we can reuse these precast girder models in our other bridges because all these geometrical model, analysis model, construction stages, and calculation report creations are parametrically connected to each other, and you can use them for your other bridges just by changing some of the parameters. So if you want to follow my work and if you want to work along with me, you can download the materials seen on the chat, and you can continue to follow. If you are stuck in any stage, we have provided you 9 steps. So I will show you the file. We will have 9 steps, and all you need to do is when you stuck in somewhere, you need to drag and drop to the Allplan civil so that you can continue from where you stuck. And in order to upload the files, again, in order to see the geometrical properties as well, in the chat section, in the broadcasting, you can see the cross-section dimensions. Also, in the PowerPoint presentation here, you can see the dimensions here, how we can create them, and so on. So please write if you have any questions about the installation, if you have any problems with the installation and licensing, so that our team can help you. So before starting, you will see 3 icons after you install the Allplan. So we will start by double-clicking Allplan Civil, and you will have options to be asked for which license to choose. If you start Allplan Civil, please choose the Civil license so that we would perform the analysis together without any problem. If you choose the Ultimate license, it will only support the geometrical aspects, so that we cannot do any analysis, we cannot use any analysis features together. So after opening it, here you can you are seeing a new model. You are seeing a model. Maybe it will be empty for you. So in order to create a new model, you just simply click the Allplan icon here and state your location by either choosing this option or a home option from here. I will now choose the C project space directly, and then I can state my project name here. In this window, you can also state your specification. As you can see, we have options to choose from Eurocode and the H2. And if you choose Eurocode, you will have options to choose from UK, Germany, Spain. And now today we will only use the general Eurocode, and we can choose our bridge type and the units here as well. After that, you can always change this from the project settings. So when you create this a new project, here you can see many options. In the work tree, we see three options for the geometry, and for the results, and for the analysis. So you can move your menus if you want in the user interface. When you use the geometrical approach, your geometrical model will be seen in the 3D model tab. And when you want to focus on your analysis model, you can see your model here. So let me start with the geometrical part, how we can model it and how we can continue. So I will check is there any question. So Stefan, you can get the TCL files from the link in the chat, or you can download it from the reminder email. And yes, there will be a recording of the webinar after the session ends. So to geometrically model, if you click to the geometry tab and the structure tab, you can see the workflow of the geometry. So you can import your DTM for your terrains, and you can model your axis. After you model the axis, you should create your cross sections, and with your cross sections you can create girder, piers, link girder for precast, such as for precast eye girders, decks for such as slabs of the precast eye girders, bodies for the abutment components like field elements, and structure connections such as bearings and the soil supports as well. And with the variations, you can variate your structural members by using the variables. So first thing first, we should start by creating the axis. And to do that, you should right click to the axis directly, and for today's simple approach, you can create a new straight axis. When you create a new straight axis, it is asking you how it's asking you the length of the line in the plan view. So if I create a 50-meter plan view, it will automatically drawn here. So after the axis is created, we would need two transversal axes for one span for precast eye girder bridges. So to attach the transversal axes to the main axis, I will now click to the right click to the axis directly and create my transversal axis 1, and I press enter, and it will ask me to set the station for the transversal axis 1. So I can see my station is at 0 meter, and the length in the transversal direction would be 20, and it will be symmetrically 10 minutes and 10 minutes. And after you create it, you can always choose and state your offset and length, and you can arrange your properties every time. So after changing anything, you should recalculate to have the actions on the main screen. I will need a second transversal axis. I right clicked again and I pressed enter. This time I will state my second transversal axis, but as you can see, you may misclick to the axis, so you can state your current axis at the specific station. In this case, we will focus on the 21st of the station. So So now our transverse axes are created. Now in order to create girders and the cap beams and the piers, we would need a cross section. We would need to create the cross sections itself. So now the axis is created. I can switch to the cross section and I can create my girder cross section by right clicking again and say new. This is new cross section. So I will state its name as a girder and I pressed enter. After pressing enter, I am double clicking it so that you would be welcome with the two main axes. One is Z axis and one is Y axis. And I am switching to the cross section tab here so that I can see what would be the functions to create the cross sections. So, excuse me. So to create our cross sections, we can use parametric lines. And what is the logic behind the parametric lines? Is our parametric lines is directly be used in the cross section, and our parametric lines is connected to the main lines with the variables you are stating. So in order to, for example, create parallel line to the main lines, I am using this function. Again, I am showing, and I can state my parallel line here. I will open the geometric properties here, and if you miss my screen here, you can always see the pictures in the material content. Here I can show. Here you can see the geometrical PNGs here. And as you can see, I stated my height of the girder, and I can always change my parametric line by only changing the value here. So I will quickly assign the other values here. I will start with the horizontal lines by using the parallel line here, and until you cancel it, it will always be repeated automatically. So I am using it again for 10 centimeters, and for the third parallel line I will use 15 centimeter. Then for the top of the connection to the slab, I will reference like imaginary 20 centimeter here, and from the bottom I will need 15 centimeter and 25 centimeter here again, as you can see from the horizontal lines. Now back to the vertical lines, I will use again the parallel line, and here you can see 50 centimeter here. I will need 40 centimeter for the bottom, and for the web I will need 10 centimeter. Then for the middle part from here I will need 30 centimeter. The reason why I am drawing these arrows like this, it is showing the direction how they can parametrically connect to the wedge line. For example, this line is parametrically connected to the outer line of the cross section. And when you click it, you can see the parametric connection here. And I will do the same one for the symmetry. Sorry, I misclicked it. Here I can see, okay, 50 centimeter, 40 centimeter, and 30 centimeter from here. And for the outer one, for the deck connection, I would need 5 centimeter after that. Now these are the parametric lines to be used to draw the boundary, outer boundary of the cross section itself, so that we would create a beam from that boundary. So to do that, I would first need a boundary. I clicked the boundary option here in the top, and I started drawing my boundary. The intersections are automatically recognized when you click near to them, so that I can continue drawing. So I am just clicking to the desired intersections. I will check if there is any question here until that point. Now I am continuing. Now if you lastly click to the point where you started, it will automatically close boundary, then the function will stop. So as you can see from here, you can activate this option and deactivate this option to check if you have a beam inside of your outer boundary. In this case, we don't have the beam, so that we need to create a beam to be used in the girder. So in order to do that, we will need to use this function, so that we would have a filled beam inside of the boundary. I am first selecting the intersection point for the unit position, then I am selecting the boundary to be assigned. You can see from the explanations always how you can be directed and complete your task accordingly. So I will check again. As you can see, my boundary is now filled, and this means it can now be used in the beams as a cross section. And I will need a second boundary. To do that, I click the boundary again, so that I will quickly draw this. And this boundary will be used to be connected to the slab in the next steps. I am recalculating again. As you can see, nothing came here to the main model, because this was a cross section and this was the reference cross section, and we need to specify in which structure members it should be used. So I will show them in the next steps, but before doing that, let me complete my cross sections here. And I will need a second cross section for the cap beam, as known as pier cap. For this, I double clicked it again, and I will use my parallel lines. After you clicking the line, the options can be activated here, or you can always use the functionalities here. So my cap beam, I will check my geometry, and my cap beam should be 1.2 meter high and 2 meter wide. So one at the right and one at the left. And I will need a reference point for my bearings connection. For that, I will need a 10 meter high, and for my bearings location in horizontal, I will create a 50 meter from here. So for the outer boundary, I will choose again the boundary. Like this. And I need to fill my boundary by choosing the reference point and choosing the outer geometry again. For the bearings connection, I should have reference points, and with this button you can create reference points so that you can state in which place you can place your bearings. So I clicked it, and I clicked the intersections again, and here I will need a reference point in the top and in the bottom as well. These are going to be used for the bearing creation, and these are going to be used for the pier connection. I will need a last cross section. Our columns will be circular, so that you can also create a new simple section, so that it would automatically create a predefined cross section for your simple sections. I will need to have the radius of 60 centimeter, And for connection, I would need a reference point here as well. And you can see for the simple sections, the structure unit is automatically created, so you don't need to create your structure units again and again. So after recalculating it, I can still see no girder or cap beam is created here. First, I will start with the creation of the girders and for creating the cap beam. So to do that, I switch to the structural member and I right click to the girders and I gave it a name and it's refreshed, and now I can select my axis. As you can see from the default, it will activate the first cross section in the list. If I want to switch it without clicking anywhere, I am going to the cross section and left clicking here so that it will update automatically. I want my cap beam to be started from the fifth station here, and I want to use as a beam in my analysis model. Then I want it to be finished in the 50. And I want this girder to be equally divided to 5 units so that it will automatically calculate. You can either specify each steps for the division, or you can specify how you can specify the number of divisions in the girder. So you can fill your structure and you can deactivate again. You can look at the perspective view like this. You can rotate by left clicking, by holding the left click, and with the mouse wheel you can zoom, extend or zoom in, zoom out or zoom in, and with the double clicking to the mouse wheel you can zoom extend. So after that I would like to create my piers, but before that, if you have come to this stage, you can always back up your project by using this button so that it will create a TCL and XML file in the project folder. I save my project like this, and here you can find the logging window if anything goes wrong, or if anything if anything goes wrong, or if software wants to warn the user, you can see all the messages here. You can deactivate or auto hide like this, or you can left click and you can make it fixed like this. So after the cap beams, I am switching to the piers and I am right clicking to the piers, and I will choose a reference point for the pier 1. So remember I will switch to the pier column cross section. Remember we had a reference point on the bottom of the cap beam. So since I said it was a reference point, I can click to the reference point so that our pier will be connected to this reference point. After clicking it, it is asking me to choose the first station. I will state this as 0. And I will choose my second station for the -10 so that it will have the height of 10 meter. And I will click to the total again and equal division of 5 so that every station would be 2 meter. I am pressing escape to exit the command, and after creating one pier you can copy your girders or piers or link girders, everything. So you should right click to your member and state the new name, and all you need to do is to specify the new geometrical points. In this case, our geometrical point was 1, and our geometrical point 2 was the height of the pier, so that I don't need to specify the new geometrical position 2. I just need to point for the new reference point for the geometrical point 1, so that it will be copied easily like this. Now the substructure TCL is done, and after that we can create our girders actually for the superstructure. But for the precast eye girders are usually linked between the 2 points, right? So they would act as a link. So that's why we want to use the link girders for our precast eye girders, so that we will specify 2 points to be connected from. So, and we would have a very huge number of precast eye girders for one bridge. So as well as the other ones, we can create the new template for the link girder creation, so that it will be stored automatically, and every time you need a link girder, a new link girder can be created from the template. So this template is different logic to direct connection. So to do that, again, since the girder was my first cross section, it chose to the girder cross section that I need, and to specify the length, I will just need to enter. In our case, I would want to have the 20 meter of precast eye girder length, so I am pressing enter. And again, it is asking me to in which division I should divide, and I enter 10. So 10 equally divided stations are created here. As you can see, the symbol T is stating this is a template, this is not an actual girder, and this opens a new window when you double click it, because it is not a member of our main structure. In order to attach a link girder to a main structure, we should right click and we should create a new link girder from the template. So I will just rename it so that our girder can be created with this name, and you would have options after you created it. As in the pier, we can state our reference point, docking point, or relative distance, or we can give absolute height, and we would need 2 points again as in the pier. And as you can see, you can either choose choose different options for the different geometrical positions. So since I will connect this link girder to the different axes, I will choose relative axis for the both points. So it's suggesting me to choose the axis. I choose the transverse axis so that I can vary it in here, and I will enter the 3 and enter, and I will specify the offset from the station point. In this case, I will state -1.9. And now the GP1 is stored. We are switching to the GP2. Now I will choose my second axis, and again the location, and again the axis, again the offset, sorry. So as you can see, we can look from the side. As you can see, it is created between axis 1 and axis 2 directly. Again, from the properties, you can state your offsets from GP1 and GP2, and you can change many other options here. So you may realize after I stated offset, it moved as the distance in here. So for the precast girder bridges, the challenge is to have many girders with the same properties. So in order to face the issue, we created for a girder as a multiple copy option, so that every time you need a new girder, you just need to click to the new geometrical positions. So for easier naming, I will delete the suffix of the one suffix of the name, and I want it to start from 2 and increase by 1. So to do that, I will go to here again. I want them to be placed to be distanced from the 2 meter from each other, so that it was the 3 meter here. Now I will state here 1 meter. Again with the same offset. Again going to the distance axis, 1 and like this. For symmetrical purposes, I will go to distance axis and say it is -1, offset from -1.9, -1, -1.9, and again -3. If you misclick here something, you can also change it from the properties menu as well. And you should recalculate it to have the action. So this was our geometrical model, and as you can see, to be taking place in the analysis model, we should do some arrangements. But before that, as you can see, precast girders are aligned to the main axis, but the cap beam is not aligned to the main axis. So to do that, we can have many options. Either you can use reference points, or in this case, we can change directly the reference Z point by changing its position in the vertical direction, like this, -3.2, so that it will be offsetted as you stated, like this. So as I said, this was our geometrical model. In order to convert it to analysis model directly, we should go to the calculation tab and say that this model can be used in the analytical model as well, analysis model as well. So here are the options for the calculation. I want for this geometry to be calculated fully 3 boolean, and I wanted to have the real calculate the real timeline as known as construction stages. And for these members, I want to have auto numbering, and we will talk about all in detail later, but we should have to check all these options. So after recalculating this, it gives us the warning, say that we want to create an analysis model, but we need a data. So every time, as I said, you need something, the software warns you, say that you should need a material to create your structure analysis model. So as you can see, it is colored in blue, meaning that none of our members has no material. And when I switch back to the analysis model, I can see all the functions are working, and it created automatically from geometrical model and considered these are the beam and renumbered them automatically. Why? Because we said that our cap beam, when we go to the stations, our cap beam should act as a beam in our structural model, or our piers should be as a beam, and everything we can select from here. So in order to eliminate this error, we should go to analysis part, analysis tab, and we should go to materials. By right clicking it, we can create a new standard for material, and I will choose general EM. So after choosing the material, I can customly define a new material, or I can import from BIM Plus a predefined materials to be used uh, in our analysis model. So from here you can see so many specifications, and from here I will choose standard EN, and for my concrete I will need C35 for my substructure and C45 for my girders. And I can use my C35 in my slab as well. And for the pre-stressed steel, generally this type is used in the pretensioned tendons. And for my reinforcement steel, I will choose a commonly used one again, and I took over the materials here, and now I can import to our project. As you can see, all the properties in the industry are predefined and can be used in our analysis model again. So after recalculating, it will still give the error because we should assign these materials to our members. So to do that, I switched back to the geometry and right-clicked my structure member and chose material here. And either it opened me a table for the material, either I can assign material from here directly, or I can drag and drop to the material name directly. So after recalculating it, you can see a different color is light for the cap beam. Why? Because the cap beam has material and the other ones are not. So I will quickly assign a materials here. For the pier 2 again. And for the link girder, we don't need to assign each individual link girder again and again because these are created from the template. Any change happened in the template will affect or result in the created girders. So I can change my material from the template girder so that it will take effect on the other girders as well. As you can see, we have no error anymore, and all the girders are affected from the template girder. So after that, we can see if we do any change in our 3D model. For example, if we change the skew of one girder, let's say we are moving our geometrical position to 2 meters, it will be automatically read by analysis model and can be updated here again simultaneously. So I will switch back to this again. So it is read by analysis model and updated simultaneously like this. And after that, for the precast girders, we need to create a pretension tendons as well. So for the pretension tendons, we need to have reference points in the cross section. So to do that, we have a function in cross section as known as point grids, so that we can group these points for the multiple tendon creations. So to do that, I press escape. You can click this and state your intersection point for the starting point. And you will have 2 directions for this. You can use all these functions until now in any kind of bridges or in any kind of structures, by the way. So for the point grids, you will have 2 directions, as I said. And for the U direction, as well as horizontal direction, we can increase the number of the tendons, and we can change their offsets in horizontal direction. I will look at my notes so that it will have this symmetry. and you can choose the spacing between them. It should be 7 centimeters, sorry. And again, for the vertical direction, the offset is good from the bottom, and I will just need to change the spacing. Now these are symmetrical, and these are adaptable to the tendon points. So to create the tendons, now we have the reference points for tendons. Now we just need to create the tendons. To create the tendons, we just go to the tendons tab and right click and say this is a new tendon group. And I pressed enter. So under the tendon group, now I can create the new tendon. For my first tendon, uh, after I click to the first tendon, it will open a tendon menu and activate the tendon menu so that you can choose the points of the reference grid points and you can create your tendons. After left clicking to your tendon, you would have options to choose between post-tension and pre-tension. It's pre-tensioned in our case. If you choose post-tensions, you would give options to the losses of pre-stressing due to friction and so on. But if you choose pre-tension, you can see how it is changing for the debonded length or transmission length for your analysis calculations. So tendon number will be automatic. I don't need to give any description here. I just need to state its material and its central area. Generally, it is 150 millimeters square. And I just need to have the transmission length for each tendon. In this case, it will be 80 meter. It is a common value for this kind of strand areas. So these are just initial. You can always change the values after your analysis model is done or calculation finish. So for the tendon one, you may see our property definition is done, and I can insert my points here again. So for this, I will choose my structure point and I will show you again. I just need to insert a 1 point for the structure member 1 and for the station 0. I will need a reference point. And for the second point, I will need to choose the last station for pretension tendons, then choose my reference point again. So that I pressed escape to quit from the function, and I can see my tendon is created on the grid point 1. So after that, I can multiply, copy and move my tendons in order not to create so many repetitive tasks. For the tendon 2, I will just simply choose a structure member and the station and new grid point, and it will be repeated automatically. And for the naming as well, I just need to do every time structure member, station. I will just repeat the process. Select the structure member, station, and grid point. So we will need maybe 12 tendons for this kind of span lengths and heights. So I will create a symmetric tendon creation like this. So 6 on the bottom of the point grids. You may realize it is always the same station but the different grid points here. So the last tendon is copied here. I will press cancel and you can see all the tendons are created in the desired locations. So in some tendons, maybe we would need to have debonded lengths. So for this we can create a demand length for the beginning and the end, and we can do them separately. Generally, they are symmetric for the pretension beams. So for the second tendon here, and for the fifth tendon here, I would like to assign a debonding length. I will just left click and open the property menu here again and state my debonding length as well. So in order to copy these tendons to the other girders, I just need to go to copy and move function and state my structural member, select my station, and select my first tendon's reference point in this case, so that all the tendon group are copied to the first structural member with all the properties. Remember, we assigned a debonding length to the second, and remember all the properties are copied to the new girder again. And for my third girder, structure member station and the point grid. And again, station and point grid. So I will check if is there any question. No. Okay, I can continue. So up to that point, it was mainly about the geometrical creation and one analysis model creation. After that, we can see how we can load our structure and simulate our construction stages. So before going to the construction stages, these were the geometrical definitions of the tendons. To assign a stressing to the tendons, I just need to switch to the analysis tab and to the tendon stressing so that I can stress my tendons in my desired loads. Analysis tendon stressing and right click will open me a new stress group. I can enter it. So if I double click, the tendon stressing menu is activated, and from here you can stress your tendons. You can assign a weight slip, or you can release your tendons here. For the pretension case, I will only use the stressing function. So in order to assign our tendons here, we just need to go to geometry and tendon, and I can collapse all groups so that it can be manageable. I will select my tendon groups by holding the shift button and left clicking to the last one, and I can drop my tendons to the analysis and stress group easily, like this. So that after the recalculation, every tendon have the stressing based on the material properties here, or the transmission length or the debonding length. For example, for the transmission length, we can see 0.8 is here. You can see from the coordinate menu. And for example, if you have debonding length, you are cancelling your tendon stressing until the point 4, and then you have a transmission length. And these are parametrically calculated, so if you change something in your material or the properties, this table will automatically activate it. And the initial force is calculated by considering the initial stressing of material and the stress area and the strength area. So you can change your force value here, or you can factor it. So okay, after the tendons are assigned and stress is assigned, we can now simulate our fabrication processes for the precast girder bridges. And so to do that, we should go to the analysis and construction, and we just need to right click, and we can see a new construction we can create, or new precast template we can create. With the same logic with geometry, you can also create a template and store your construction so that it can be used repeatedly for the multiple number of girders. So in order to create a precast template, I just need to name it. and you see the same symbol as in the link girder is appearing here. And this template is going to be used to simulate the fabrication and the lifting process of the precast template. You can simulate many more things, but today we will focus only on the fabrication and the lifting processes. So to do that, I will right click to the precast template and say this is a new phase. And our first phase is going to be fabrication. And our second phase is going to be lifting. So as you may know, precast girders needs to be simulated in many stages. In fabrication, you would need different support conditions, different press stressing. In lifting, you would have hooks in different locations so that you would need to deactivate and activate supports in different regions. So when placed on the construction site, the support conditions are again changed in different timelines. And all these things require repetitive tasks for each girder. In order to eliminate that, we created a precast template in the 25 version so that you can simulate these things easily without having to do a repetitive task again for each girder. So I double clicked to the fabrication phase, and I switched to construction phase. So to do that, we have many options from the concrete, pouring, mounting of girders, uh, activating bearings and springs, but for the fabrication process, we will focus this menu, precast menu, I mean. To create temporary supports, we would need to use supported, and when I click this, it will come here, and so that we can create a temporary support in the fabrication phase. And for lifting phase, we would need to remove our temporary supports from the previous phase and activate a new supports for the lifting for the hook positions. So in my cross section, I would need again the reference points for them to be connected here, so that I will change the cross section. And for my bottom connections for my temporary supports, I would create a one reference point, and for the top I will create one reference point. You can left click them and activate them and rename them as your preference. In this case, I would say this is a P bottom and this is P top. From here, I can go back to the switch to the fabrication and say that my supported function will need a reference point in the bottom. I can directly say this is going to be referenced in the bottom, in the station in the beginning, at the beginning, and I can specify my rigidities for the temporary supports in each direction. In this case, these are for translation and these are for rotation. So I will quickly use some rigidities here and maybe small rotational fixes in the fabrication. And for my second position, I can again use the same reference point but different station in this case. Why? Because our girder is created from, I can show it from here, from the actual girder, sorry. You can see it is starting from 0 and ending in the 20th. So in the fabrication phase, I can say my second point is at 20th section, and I can again say this is going to be simply supported, so I will release one translation rigidity, and I'm assigning a small rotation rigidity again. And for the lifting process, I should need to remove the remove the supports from the fabrication, so that I will just rename from the reference point. You can assign any name for the removal process. At the station 0, it will be activated as this load case. So for the second removal, it will be activated as this load case, and at the station of 20. And again, for the lifting process, I can now change my reference point. As you may remember from the girder one, this one, from the girder code section, the top reference point was this, and I can go and assign again, in this time, for example, second station, and again the rigidities as we design. I would like to again have pin support for this with some rigidity in the rotation, not the last station but the station before the last one. And I would release one translation for roller support, pin to roller connection, and recalculate our model again. I have no error, so this will be going to be used for each girder for temporary supports activation and deactivation. But for the fabrication process, we have a function called as Precast G here, as you can see. And what this does is, you can, after opening it, you can left click on the empty window and you can press F1, so that it would give you a detailed explanation from the help menu here. But I will quickly explain this. So for the Precast G menu, you can simulate the stressing, as you can see here. The durations, casting durations you can specify. And after that, transfer durations. You can simulate the casting bed, and you can state your testing for the shrinkage, for example. And in order to simulate the casting bed, because Precast G is requiring a bed environment for the casting so that it would calculate the creep and shrinkages correctly, and I am pressing OK because it is asking me to have the casting bed, and we can simulate this casting bed with the geometry and placements. After going to the geometry and placements, I am right clicking new and new casting bed here, and here you can see it is opening a property window, and here you can see you can simulate the release of tendons. I will say gradual. You can simulate the heating and cooling cycle and simplify temperature loads according to the Eurocode 2. So in order to simulate the heating and cooling cycle, we would need a table. So in order to simulate the real production timeline, some of the contractors are steaming their precast girders to speed up the process and in the fabrication. So we can also simulate that. And in this case, x-axis will be the time and y-axis will be the degrees in Celsius, because we chose the metric system. So when starting, I would assume we are starting at 20 degrees Celsius here. For the first hour, I will say we are heating our environment to the 60 degrees Celsius, then decreasing again to 20. Then at the end of the cycle, we are saying it is still going to the 20. So we can attach this table to the casting bed so that it will create a connection to the Precast G function. So all we need to do to simulate the casting environment is to have two definitions. So I am pressing OK. And for the support functions, we didn't need to have to attach to our geometric models or the analysis models for the girders, but for the Precast G functions, we just need to assign in which girder is it going to be placed, calculated, and in which tendons are going to be stressed. We need to specify that. Since this is a template, we will need variables for this. So after left clicking to the Precast template, I would add a variable. You can see we can vary the template Precast construction with just variables. So with the text variables, we can change the girder names between, we can activate the girders by considering their names only. And for example, we can assign a duration of lift and we can vary it between each girder. Their lifting process will take, for example, 25 days, but we can vary it between each girder easily by using these variables. So after creating the variables, we just need to go to the assembly window and right click and new, and we would say for our precast girder precast G function, a member with the variation of girder with the variable of girder will be activated under this construction process, and we can go to the and right click and new, and we can activate our tendon groups. So tendon groups will be left empty and it says a warning here, and for each girder activated from the member named girder, each tendon will be automatically recognized and activated by using this template. So I will just recalculate it and to see if there's any error now. And so our template is finished for the Precast template. So we will use this template on the actual construction to simulate the fabrication and the lifting processes for each girder. So I will now not use the Precast template. Now I will create actual construction. And after creating it, I will choose a new phase and say that this is.
Ayhan, I'm sorry. Maybe something is wrong because we can see only zoomed 3D model and we don't see the full screen, at least on my side. I don't know about others.
Can everybody see?
Just a part of 3. So we see the model, but not the full.
I actually can see it. Okay.
Stefan can see. Okay.
Okay. Maybe it's on my.
So okay, then I will continue. So for the substructure, I can create a new phase. For superstructure, I can create a new phase. But first, I will show you how to activate them on the real timeline by using this real-time construction. So I create a phase called substructure. And as I said here, these functions was for the template constructions. Now here is the actual activation constructions for the concrete. This concrete task can simulate the pouring and curing of your concrete. And for the activation of the supports, we would need to use in support function here. And for example, I need to activate my if I need to activate my pier, I will just need to state their start date and the duration for the curing and everything, and I should go to my assembly list and choose a one member and press enter so that it will be activated on the day first, and it will be casted by using the concrete task for the 14 days. Or I can directly drag and drop my member here after left clicking and dropping. It will also activate the same member. You can some of the members may have multiple structure units. You can choose which structure units to activate or not. If you don't choose anything, everything in the structural member will be activated. So for the support activation, I should give it a start name. And for the support activation, remember we didn't assign any supports to our system. So if I recalculate this, it would create instability, resulting in negative pivot, so that it is saying please activate your support so that it will create structure instability. So I will need to define the structure connections for soil support, and for the soil support one I choose a fixed, and then I will deactivate the hidden option, field option. So I can choose my reference point, then I can choose my cross section, so that my soil support for the fixed soil support will be connected to this reference point by using this cross section. I will repeat this again. Right click new soil support to fixed, and first the reference point here, then to cross section, so that if I recalculate it, they can be connected to the analysis model. But notice there is still instability in the system. Why? Because we didn't activate them on the by using the support function. I will activate them by using drag and drop again. I chose them with control button or holding the shift button. So all we left is the warning say that there is still so much beam elements on the system. Please be careful to activate them or not. So all we have in the analysis model is now the piers. We can check from the results, and we can simulate their self-weight summations and to see if they're activated or not. There you can go to the results and the 3D diagrams and choose load case to see if the axial forces diagram or the moment are activated or not. As you can see, not all the other members are activated, so that we should activate them as well. So for the cap beam, after these are activated, I can still use a concrete function. For the 14 day, let's say this is going to be last for 12 days, and I will activate my cap beam here. But this will again give me error because there is no rigid or bearing connectivity between the pier and the cap beam. In order to eliminate them, we can use a different structure connections, and say we can use rigid connections. So we can connect them from unit to unit. My first connection would be from this cross section to second cross section, and my second connection will be from again unit to unit, from pier to cap beam cross section, so that after recalculating I can say these are rigidly connected and these can work together, as we can see from the self-weights shear diagram this time as well. So after the substructure is activated, we can activate the span, and here we can call our construction templates, precast templates, To activate our girders, we should use special function as known as install or mounting concrete girders. And before that, we will need to have a supports again. I will right click and move up, and these can start after these are finished. So I can assign a days for example, starting from the 30, and this can be activated in the day 30 as well. So I stated here that fabrication will last 2 days, and the lifting, for example, I didn't state any. I can say that this is the local mount SMD, but if I want to reference my start date to the mount, it will calculate from the last day, and it can be activated from the last day as a mount. So I switch back to the span, and I will say that I will need to have a bearing connections and support connections here again for the precast girders. So I will start with my bearings. So for bearings, we would need a custom definitions. In this case, this is representing the vertical one. Again, in any menu, you can press F1 and read the definitions, by the way, for the each other structure connections, and see the detailed explanations here as well. So I will state I would assume these are elastomeric bearings, most common bearings for the connections, and I can just very small assign in one direction the rotations, just very small for the bearing one. And for bearing, I will need to use one reference point. In this case, a reference point cap beam, and I will choose one cross section. I should quit the, and I will need to do this again, just so I would have custom bearing. I cannot choose right now. Let me recalculate it. So if you encounter a size problem, maybe you can export and import again your TCL so that it will refresh. So this happens to the presenter, sorry. So for the new bearing, for the first reference point and for the first cross section, and for the second cross section, you will see a new connection can be created, and you can always change your rigidities here as well. You don't need to specify from the beginning all over again. And you can see the connections, the locations, where is the rigid connection 1 and where is the rigid connection 2. And I will just need to assign this quickly for the bearing 1 and bearing 3. For the bearing 4. And for the abutment representation, I can use a soil supports, and I can complete my soil supports like this. So in order to copy the rigidities, we can right click and copy our strict stiffnesses to the new function so that I copy it to the bearing tool, you will see these have the same stiffness values. And we can copy this quickly like this. And from bearings to soil supports as well, because these have the same spring stiffness. I couldn't choose. Like this. So for the constructions and for analysis and constructions, we would not need to go to the span, and by choosing multiply by holding the shift button, we can drag and drop here. And I would need to drag and drop for the soil supports, and I will recalculate this, and after that it is giving me a warning: you didn't activate your members, so that I would activate my members according to that. So for the girders, again I can choose from the here, or I can drag and drop here. But for the fabrication process, for special for the girders, I can multi-select them and say that these have template constructions, and this is going to be considered as before the day of 30. The stages before in the fabrication will be taken into account and carried to the final results. So after recalculating this again, so I should check what is wrong, and maybe I can import again in order not to lose time. So I can insert on-site construction span, so that we can continue from the span one. So after activating these precast templates for each girder will have a history before the mounting to the real site. So to simulate that, we call this a submodel, because this is main model in the analysis model, and you can simulate your results here after activating them. But for the submodel, you can go to construction and precast tab again and activate your girders. After activating it, the submodel will be opened, and for each individual girder there would be a different submodels. So for each individual girder you will see the load results in here. For example, when I am lifting, what will be the moment result, and when, for example, when I am stressing, what will be the moment result here, or the dead load moments, or even the last results for it. You see, this is the lifting process for the moment diagram. So if you want to switch to the main model, you just need to click this one, and you can continue your analysis again. So after creating these precast girders, I want to mention about how we can make the system composite by using the deck. So I already showed you how to define the cross sections with using parametric lines. So in order not to lose time, I will import the TCL file from the workshop, and you can import your cross sections from other projects as well, like this. So I will import first my sidewalk, then I will import a TCL file for the deck. So that I can create a new deck member and make the system composite like this. For each precast girder, you would need to have a different deck member like this as a beam unit, and you would need one empty boundary to be represent the girder connectivity as a Boolean functions here for making the system composite. And since we have a deck member, I can go to my structure members again and create my new deck. So I will press enter. It will suggest me to select axis. Now I will switch to the deck cross section, and my first point would be 0.5 as the beginning of the precast girder, then last point to the 20.5, and total division of 10 meter maybe. And remember, blue color means there is no material in the system. And in the deck cross section, different than the beam members, we will see a load units here as well. So green color means they are load. They are not affecting the moment of inertia to the system. They are just going to be used for the load assignments. And I should go to deck material assignment. Then I can choose every unit in the structure system by holding the shift button, and I can assign the same material to every structure unit. And I can recalculate this again. And if it will give me a warning that element is not activated, please use these functions to activate it. So, but before activating it, I want to connect them as a composite in one section. So, with the deck options, I can have a booleans and say that we are choosing them. We are choosing a boolean type as a haunch connection, and from second unit, from beginning to the end, I will explain in detail now. My first girder will be connected to the system by using the boundary 2, for example. So I will repeat this. You see, for the left operand representing the deck connection. So for my deck connection, there would be a second beam unit. And if I switch back to the booleans of the deck, the second structure unit is from a deck unit and from beginning and to the end. And for the right operand, it is representing the girder structure. And when I go to the girders cross section, I have to use boundary 2 to connect the girder and the deck again. This is just a representative girder. It will be eliminated after the boolean function is operated. So for each girder, I can state beginning and end, and for the connection. And since all the girders have same cross section, I can use everything same again, like this. Again, boundary 2, and last one. Why I will show in a minute. And for the last girder, boundary type, and same boundary 2. And when we go to the deck cross section, we can see our beam units are 2, 5, 8, 11, and 1, 4, and 7, and 10 will be used as a girder when after they are being composite. So, as I said, in order to make them composite, we defined a boolean functions so that now we can activate our composite concrete function so that they would be composite units. Maybe this should start from day 40 in your preference, and this should last 5 days, for example. And I am just choosing which unit should be activated from the deck. And if you press enter, it will consider all the stations automatically after choosing it. 2, 5, 7 and 11 is activated as composite, we are saying here. And after recalculating, we can see tendons are not recognizable in the system. Why? Because our main beam is now not the link girders. Our deck will be recognized as the beam in the system after being them composite. So from our link girders, we should say that this will be just a reference for our composite sections, and this will not be used as a beam. Rather, our deck will be used as a beam. So to do that, we should correct every assignment to the system. For example, we should correct the bearing connection if you want to make the system composite. Like this. And sorry, I will correct this too. To 5 and sorry, first member was 11 because it was the bearing 1 was here, so it should be 11 in the deck member. So it should be here. I will show you again. It should be connected to this part, bearing 1. Eleven, 8, and last station 5. And as you can see, you can always change the reference connections from here. And for the solid supports, they should also be connected to the deck 1 from 2. From this time again, starting from 2, 5, 8, 11. And we can recalculate it. So that all the members can be activated as composite in this case. So we made the definition for the composite, but as you know, deck is connecting to the girders transversely, so deck is also need to be simulated transversely and needs to be analyzed transversely as well. So to simulate that, we have a function as known as insconc, a second insconc, and this is simulating mount concrete girder fictitiously. So these are I will move this to the end. This is simulating the transverse connection between the girders. For example, I will start this from day 50, but in order to activate that, we need to make our deck with auto grillage definition so that it would create a grillage. I will turn this auto option on, and our grillage cross section would have, for example, C45. This is a transverse member, by the way. And from here, we would need a transverse connection cross section. I will just import from the project again. Like this. This is a kind of cross section to connect them transversely, actually, with the value of random value. So in order to connect them transversely, I would give them a greenish cross section, and for the height, this is the same random value that you saw in the cross section, and for the automatic greenish definition, precast girders from 1 to 4 should be connected. Let's say it will be divided into 2, and 4 to 7 should be connected, and they should be divided into 2. And 7 to 10 should be connected, and they should be divided into 2, because as you may remember from the cross section, 1, 4, 7, and 10 is representing the precast girders. So this created a new beam in the transverse direction, so that we can create, by using this function, by using the assembly as known as Z-beam deck. Press enter and rerun it again. And after activating it, we see no warnings, and we can continue to assign additional loads to the system. So for this, for example, we will need additional super dead loads coming from the asphalt and the sidewalks, for example. For super dead loads, it should, let's say it is starting at the day of 60, after 10 days after the mounting. And we can create a new load case for this. And we can say that this is super dead load, and if you choose the load case to add it to the super dead load, it will be counted as a mess in your dynamic calculations as well. So that is the difference. And after activating the load case, we have vertical, horizontal, and vertical, horizontal point loads, and a settlement, everything is activated. To do this, to do super dead loads, I would activate the line load in vertical direction, and I will assign a composite member here, and I will press enter. So I assigned an assembly, but I didn't specify my load. So this will be automatically recognized from the deck cross section and say that these load units are transferred to here as automatically from the material properties and the geometrical properties as specified in the deck cross section. As you may remember, I said the green ones are the load units and have no effect on the inertia of the system. And to do this, to do the other ones, I will just copy them again 6 times, because we have 6 loads in the system, like this. And for each different structure unit, we can say, oh, I want to assign an asphalt load to the second beam, and I assigned a second beam and simply change my asphalt, and it will be activated here. Don't worry, the precast girders are connected with Z-beam with grillage option, so that it will be distributed evenly. But in order to simulate this accurately, I am activating the loads close to the member, close to that specific member. So for the last composite, 16, and for the sidewalks, left sidewalk is close to the third composite unit, so it will be activated like this. And for the right, it is close to the right girder, and my composite unit, my load unit, is activated on the very right hand side. So after activating the super dead load, you can see from here, super dead load cases are also coming here. So as you may see, we didn't activate any of the super dead load, self-weight, and pre-stressing in specific construction. For this kind of calculations, you can check our calculation options are here, and auto-generate calculation tasks are chosen for that reason. So that every time you activate one function, for example, as concrete function from construction, these load cases are automatically generated. So after super dead load, you may need to have moving loads. I will also quickly show this, and then after that we can jump to the combinations, superpositions, and checks, and we can finalize this workshop. So for the lane sets, we have an option for analysis traffic loads, and we can say a new lane set here, and we can open this. We can deactivate the 3D view and assign the assembly, and we can activate the deck. So I will just assign a new offset to the line load and say that this will be offsetted to minus 2.6, and I can assign a lane for 3 meter first and 2.2 meters as second. We will have two lanes, and in order to align them to the asphalt, we can use this option and choose the parametric line of the asphalt so that it can be aligned automatically. And from the Eurocodes for the load trains for your truck loads, you can directly import your tandem systems, for example for uniform load systems, so that you can use this in your calculation. And don't forget to activate the autocalculate influence line so that this line loss can be checked for every member for the most critical station. And we need to combine these lanes with the trucks, and for this we have superposition. If you double click to the superposition, we can see how we can integrate these lanes. Because we have two lanes, and we sometimes not loaded is the most critical one, and sometimes loaded is the most critical one, and we can combine them by using superposition approach. For example, for two lanes, lane can be connected to the 1 and 2, and lane 2 can be connected to 3 and 4, and TS300 can be connected to envelope 3, and uniform node can be connected to this one. So that I am trying to say here, this tandem node can be on both, maybe on both lanes or not on two lanes. And after that I will combine this again. So if I combine them after I stated the lanes, I can change like this, and I can change like this. I can change their names here. So in here I can say that as you can see, they are either added all the time, or one of them is most critical, or function is doing that. Adding is summing them at no matter what, but the AND function is either none of it, or one of it, or the summation of it. So that's why I am choosing the AND functionality here. and I am recalculating again. These superpositions are different than combinations because for combinations, if you want to do this approximation, you would need pages of combinations just to simulate the one lane is critical, two lane is critical. But in superposition, you can simulate this. But for the combinations, we can say a combination table by after right-clicking, and it will open a new combination table. And from here, we can see the all load results coming from the on-site construction. Self-weight sum and super weight sum will be our permanent loads we can drag and drop. Creep and shrinkage sum will be our time effects. Pre-stressing will be our pre-stressing. Variable will be our tandem loads and the uniform distributed loads. I will press escape. Here, and I will import creep and shrinkage again, and in here I can choose my combinations, for example as characteristic, and I can give the factorings as here, and for the variable loads I can continue factoring as desired for the Euro code, and for frequent I can do the same, or I can copy them under here. But for frequent, for the variable loads, it will be different for the tandem and the uniform loads. For example, for QoS permanent loads, no variable loads would be in the system. So I will assign them as 0, and we would have, for example, a ULS loads like this. And I will give the factorings here. And maybe you have second ULS load, different combinations, and these values are taken from Eurocode. But as you can see, you have two ULS slots, and you can group them each other actually by doing so. You have 5 groups here. You can rename, this is the ULS group, and this group will be evaluated under this group name for the checks. And I will recalculate this again. And there is no warning. We can see all the results are coming here, but for the load cases. In order to activate to see, we have load cases and envelopes, but we cannot read our superpositions or combinations in the load cases. In order to activate them in the load results, we need to have one phase as a last day, and we need to use these superposition tree functions from here to call it our superpositions. And I will quickly wrap this up to finish the workshop. In order to explain the checks in detail, and we need to activate combinations as well. For the combination group, we need to use comb group function, and this should be in the last day as well. And as you can see, you can call your envelope from the ULS group, and if you don't state the day, it means it is in the last day. And for the individual combinations, you can use comp_row. For example, you can write definition and you can call your combination. And frequent combination is C2. I know from the combination table, and this is quasi permanent C3. We already called the combination group for the ULS, so we don't need to activate it in here. But if you want to activate them individually, you can activate them individually with the comp_row. So after activating it, you can see all the superpositions. You can see them individually or the characteristic loads, ULS groups, load results, and everything. Also, results can be seen as 3D diagrams, 2D diagrams, like this. You can separate one single load result and from the load case. For example, I should activate it. I should assign a assembly. This is 2D diagram. These are tables, and you can see your internal forces or stresses in the table format as well for the elements. And we will talk about design and checks, and you can even see the influence line analysis from the chosen load train. And from the vertical analysis, you can see the which tandem is affecting which. So my graphic card doesn't like me today. So you can see the individual influence line analysis like this. So after making the combinations and seeing the results, we can create a new phase for the checks. For the girder, for the single girder, we can do automatic design for the reinforcement. But for the composite sections, currently we don't have an automatic design for the reinforcement. Automatic design means in the design and checks, we have functions as code design and code check, and linear stress for the stress visualization in the report, and fatigue controls such that. But I will today only focus on the code check and the report creation, report calculate creation. As I said, for the single members, for single structure units, not composite units, we can do code design automatically. But for the composite sections, we cannot do design in the current version. So after choosing the checks as a final day, I can import a new task, and I can say that this is reinforced check. This will be a result name. Again, if I don't specify any day, this automatically means it is in the last day. You can choose what type of check you would like to do depending on your specification. Today I will only focus on the flexure and shear for now, and you can specify your and call your combination groups here. After doing so, you would need to assign an assembly from any place of the girder. In this case, I will do the calculation for the, for example, middle part of the second beam, and I will do the design. I will do the check accordingly. But I should have a reinforcement as a property set, and in any case, you can. It is warning me to group my girders for the better evaluation for the anchorage tasks and for the assemblies, and I should group each girder so that it will not be mixed in the checks. So this first 3 structure unit is for girder 1 and this is for girder 2. I can continue, but this should be enough for the check evaluation, and I group them. And then after recalculating this again, I'm trying to show you what kind of warnings the software and how would you solve it in the case of warnings. So it is giving me the warning for the anchorage zone calculation. We would need more stations, and why this is because remember the tendon stressing. We have a transmission length coming from 0 to actual pre-stressing load, and for the tendon 2, for example, we have a transmission zone starting from 4 to 4.8, as I mentioned. So it is better for anchorage calculations to be evaluated if we have additional stations in between. So in order to do that, I just need more stations in these locations. So I would add a station for the first and for the fifth. These are the middle of the transmission zones. It doesn't need to be exact middle, it just needs to be in the transmission zone for better evaluation. And I will cancel it because I added a new stations to the member, and I should create my groups again. I pressed escape to abort the calculation. And for my groups, I can select them again and apply group to the subsequent stations, and so that it will know which girder is which group for when checking. So I am looking at the info level, and the anchorage task will be done successfully after giving to the system enough stations. So it is warning us again, the composite section is not done according to the code, so that we would need to define a property sets here. So the property sets can be anything from stress point to temperature points, from reinforcements, exposure zones, joints and shear locks. So for this evaluation, in today's evaluation, we would need joint. And in this case, we need a beam unit and joint type as specified in the Eurocode. In this case, I am choosing smooth one. And we would need an additional boundary here. I pressed enter to finish my drawing, and I would go to the joint one again by left clicking, and I can say my joint will be here for the specification checks from start to end. And additionally, I will draw quickly a reinforcement. I will draw a quickly for the reinforcement assignment. So for the reinforcement assignment, I will need a boundary like this, and we have longitudinal shear and the torsion types. And for the bottom reinforcement, I will need reinforcement for the structure unit 1 and the boundary 4. As you can see, it is activated, and I can assign its material here. You can specify the diameter or the reinforcement area or even the positions from beginning and from the end, like this. And I can recalculate this again.
Oh, yes, we can see the broadcast. Everything's okay.
Okay. So after that, the code check started and it evaluated our specified section for the flexure. And if I switch back to the 3D model, I can right click and I can see my check report is activated for the flexure and shear, and I can select my member in order to create automatic reports just for the flexure. And as I showed from the system, there are many possibilities from the code checked depending on the H2 and Eurocode. And for Eurocode, we have many national annexes, like I can show it from here. For Eurocode, we have British, German, Spain, France, Austrian, and Poland national annexes. And we have H2 for now. And for the load and checks, I should show this. You can edit the design code parameters here, like this, or either manual, or you can click restore to have the values from the Eurocode 2 directly for your concrete structures. And that should be it for the workshops topics, but I want to mention also about the reporting. So remember, you can store your 3D diagrams here by choosing you can specify a new view for your reporting purposes. You can say these are my diagram and I stored it here, and you can even export to the Word. This I can say it is also parametrically connected, because these views are restored no matter what. When the model is changing, they will be updated automatically. And also you can compare your diagrams either in 2D or 3D. I can say I can create a new series. For example, actually you can compare anything. I want to compare my self-date moment diagram with the self-weight diagram, for example, for the same thing, and like this. Or I will want to create a pre-stressing comparison like this, for example, or the superdated comparison. So in the same diagram, you can compare anything you want. Even we can compare it with the design and checks in the same diagram. For example, we can see our capacities from here and compare it with the loads, resistances like this. So you can store this and create your reports automatically. And after finishing all this, you can copy your model and export it once again, maybe saving as different name. And for your other bridges, you can change your access, and it will be all parametrically connected. Sorry, Jack, you want to say something?
No, it's okay. It's okay. Sorry.
Sorry, my bad. And for the For bigger bridges, for example, for different spans, you can copy and change one or two parameters and your new bridge is done. Actually, it is a very powerful tool because we made so many temporary works in the submodel and transferred them to the main model from the precast template. Then we visualized how they can change the when you change the geometry, how they can affect the analysis model directly and simultaneously, and we could even create reports for this. So it is that easy. If you have any questions, we can talk. Sorry for it's longer than expected, but if you have any questions, please raise your hand and I can unmute you.